Welcome to the revision video for C3.1. So we're going to start with relative formula mass. So relative formula mass is sometimes abbreviated to RFM, and it's the sum of the individual relative atomic masses. Okay, so to use an example, H2O. So if you look in the periodic table, water. If you look in the periodic table, water is made of H2O. So in the periodic table, hydrogen is the two numbers are 1 and 1, and oxygen, the two numbers are 16 and 8. So the relative atomic mass is the biggest of the two numbers. And that 2 means 2 hydrogens, so that becomes 2 lots of 1 plus the biggest number of oxygen is 16. So 2 plus 16 is going to be 18. So the relative formula mass for water is 18. The empirical formula is the simplest whole number ratio of atoms of each element in the compound. Okay, so if we have something like C3H6, then we're just simplifying it. So if I had the fraction 3 over 6, I could easily simplify that by finding the highest common factor, which in this case is 3, and I divide both by 3. So 3 divided by 3 is 1, and 6 divided by 3 is 2. So we quite happily simplify that 3 over 6 to being 1 over 2. So for empirical formula, the same thing happens. So this 3 here and the 6, the highest common factor is 3. So the 3 becomes a 1, but if it's a 1, we don't write it. And the 6 becomes a 2, so it becomes CH2. So if I had, for example, C4H8, the highest common factor would be 4, so that again would become CH2. Right, so pure means only one type of chemical. So it could be just one element, or it could just be one compound. And impure means a mixture of more than one element or compound. So how can we tell from melting points? So if we draw a graph, so if we get a solid and we heat it up, then when it melts, we will get this plateau, then it will start going up again. So from this, we can take this to our y-axis. So this y-axis is the temperature, and this is the time on this axis. So this here would be the melting point. And if something's pure, then we get a sharp melting point. So it melts at a very specific temperature. So within 1 degree C. And we can also compare it to known substances. So I know ice melts at 0 degrees C. So if it's pure, it will melt exactly at 0 degrees C. If it's impure, then it will melt over a range of temperatures. And it will also melt at a lower temperature than the pure substance. So this is why in the winter, when we want our ice to melt, if we put grit or sand in it, then it will lower the temperature, and therefore at 0 degrees C it will melt. Right, so filtration. So if I'm filtering something, I'll have a filter funnel and a filter paper. Alright, now we put that into a conical flask. So the solution that comes through we call the filtrate, and the solid that's left on the filter paper we call the residue. And depending on what we're doing, sometimes you want the residue and sometimes you want the filtrate. So how does this work? So it works because the filter paper has holes in it. Okay, so there's holes in the filter paper, and they are small enough to stop the residue going through, but large enough to allow the filtrate through. And that's because when the solvent has dissolved the solute, so the solute is in very small particles when it's dissolved. Right, so solution definitions. So solute is the substance that dissolves. The solvent is the liquid that does the dissolving. The solution is the mixture of the solute in the solvent, and also a saturated solution is. So a saturated solution is where the maximum amount of solute is dissolved. Right, so crystallization is where we get my pen to write at an angle, at the right angle. Right, so crystallization, so you can write at an angle effectively, so I'll just do it across. Right, so crystallization is where we're trying to isolate a solid, and we're trying to get crystals of a solid. So what we want is crystals. So what we do is we take a solution in an evaporating basin, so we take our solution, we heat it up, and when we do that, some of the solvent evaporates, and we get a saturated, so we do that until we get a saturated solution. And once we've got our saturated solution, we let it cool, and when we do that, crystals will form, and then we can filter it, and then we can dry the crystals. So we leave them to dry on the windowsill normally, or sometimes we can put them in an oven. Okay, so simple distillation. So we use simple distillation when we want to separate a solvent from a solute. And what we do is we have our flask here. I'm going to try and draw a Bunsen burner, so we heat it here. So this is our solution. The solution is the solute dissolved in the solvent. So we have, excuse my bad drawing here. So we have a thermometer here. I apologise for my terrible drawing. So a thermometer there, so you can measure the temperature the solvent comes off at. And I'm going to try and draw the condenser jacket here, but I'm terrible at drawing. So this is my condenser. This has the water coming out of it. This has the water going in. And then we have a beaker or something here where we collect the pure solvent. So what happens is, so the solvent has a lower boiling point than the solute. So we heat it, the solvent evaporates. And then when it hits the condenser, which is cold because the water keeps it cool, so it then condenses in the condenser, and then it drips down into our collection vessel. So fractional distillation is, so it's similar to simple distillation, but we use this when we've got a mixture of two liquids. And it works because they've got different boiling points. So the one with the lowest boiling point will evaporate first. And the difference is that you have a fractionating column. So the extra thing, so between the flask, so you still have your heat here, you've got your mixture there, but here, and again, apologies for my incredibly awful diagram. So we have a fractionating column here, and because that has a high surface area, you'll get more condensation on it, and so you'll get a better separation of the liquids. Right, so paper and TLC chromatography is the same principle. You have a beaker. In the beaker, you put either your paper or your TLC plate, and that's the stationary phase. And then we put in it, at the bottom of it, we put our solvent, which is our mobile phase. And we draw a line in pencil. It has to be in pencil, otherwise it will dissolve. And then here we put our mixture. And then as the solvent goes up the stationary phase, the mixture will separate out on what we end up with. So there's our original line, and that will separate out into different spots. And the number of spots tells us